Hi friends, let's talk about Fourier transform infrared spectroscopy. So we know that infrared spectroscopy gives us the information about the some functional groups present in the molecule. So by this spectroscopy we can determine molecular structure of unknown compound. So infrared spectroscopy actually works with infrared radiation. So infrared radiation is a kind of electromagnetic radiation where the range for this kind of radiation stands like 700 nanometer to 1 millimeter. So from this table I want to mention out one thing. Here you will see different kind of radiation and wavelength and frequency and photon energy. So if we go gamma through sequentially X-ray, ultraviolet light, infrared, so we will see there is a higher photon energy or higher frequency or higher wavelength. So in electromagnetic spectrum, when we will get such kind of wire, we will get higher energy from the light. So in infrared region we have three different IR region. One is near infrared region, which exists between 700 to 3000 nanometer, and mid infrared exists between 2.5 to 25 micrometer, or far infrared stands for 25 to 1000 micrometer. So if far infrared, actually we can't see any spectra because it is so small. So that's why we use mid infrared, okay, for detection of organic molecule. So here how this wave number we can expressed by this equation. So we know since IR radiation, IR in spectroscopy is IR radiation, so it unit has wave numbers. So here we see there is a C equal to mu n lambda. So C, you know, C stands for what's speed of light, okay, and mu is frequency. Like here if we see one graph is here, so from this to this we have different wave cycles, and these wave cycles per second can be expressed as a frequency, and this range we can define as wavelength, okay. So from this light we have this wave and we can get the wavelength, and once we have the wavelength we just will convert this wavelength into wave number. Normally it can be expressed 2 by lambda or 1 by lambda, where we will get the unit per centimeter. So since already I told you that spectroscopy deals with a organic compound where the higher photon will be interacted with our sample. So how it is happen actually? So one thing, how it is happen. So here we have IR spectrophotometer. So here in IR spectrophotometer, it has in the inside of the apparatus we have one moving error, one moving mirror, mirror. So when we will pass through this this IR radiation will pass through this mirror, the light will be spread in So once the light will spread to our sample, and this light, for example, we have here 1 hertz light, or 2 hertz light, or 3 hertz light. Okay, and this 3 hertz light will, we are actually, this kind of different photon or wave or wavelength will be radiated to our sample. When our sample have same kind of energy, it will absorb, for example, it will absorb 2 energy, because the same frequency is present in that compound, so it will absorb, it will not get detected. And the other light, 1 or 3 hertz, will pass through this detector. Okay, for example, if we draw the formaldehyde here, so we'll see that for example, here maybe we have 2 hertz, this 2 hertz. Here, for example, here we have maybe 4 hertz. So it will directly go to the it will directly absorbed by the molecule, and maybe it will pass and this 2 hertz will go to the pass through the detector. Okay, and after that we will everything will get the in spectra. So what is happening when we will give the energy, this kind of energy, to our molecule, it will be vibrated, because when you give something as energy, it will be excited. So this excitation we can express as some vibrational motion of this molecule. So in IR, when you will give the IR radiation to an organic compound, it can be vibrated in many ways. Like it can vibrated in like here I have already seen here. Normally they can vibrate it in 2 different ways: stretching and bending. So when stretching will happen, so in stretching, normally, for example, we have spring. So this spring, when you when you will play with this spring, you will get like relaxation and compression. Okay, so in stretching we have 2 different kind of vibrational motion. One is symmetric, one is asymmetric. So if for the methylene groups, we have here 2 different kind of CH bonds. So for example, heat here in for this symmetric symmetric stretching, it will be maybe the bond length will be increased, this bond length will be decreased. So basically in stretching it works with the bond length. Okay, so in bond length. And another thing is in bending, so in asymmetric will happens in opposite things. For example, this bond length will be increased and this bond length can be decreased. Okay, and bending, we know that in organic component, not only we have the bond length, we have also the bond angle. So there will be a different kind of deformation of bond angle. Okay, so in bond angle we have like in plane bond angle and out plane bond angle. In plane, when you give the energy for some kind of bending means bend, something is not stretching. Here it's not it's not like a spring, it will be bends in the round. Okay, so in bending, scissoring, you will get like it moves back and forth. And in So in rocking it will be happen like it will be happen in the movement of these atoms, this angle between these two atoms will in the same direction. I mean it will bend like if we see here it will like bend in here same direction. Okay, and in wagging it can be, it will be obviously wagging and twisting will be out of plane. I mean they move up here, they move up for totally out of the plane. Okay, so one thing is I want to mention, it depends on totally in the dipole moment of this molecule or compound. So how we have it, how we know the dipole moment is depend on electronegativity of this compound. So like here if we have dipole moment, we can determine from this equation into the where E is the charge of this electron or atom, and D is the bond length. Okay, this bond length, and this charge will be like from here if we see 2.1, so and it is 2.5, so dipole moment will be so here dipole moment will be obviously more from towards the carbon direction, because carbon will pull the electron from the hydrogen because it has a greater charge than hydrogen. Okay, so from this situation we get the dipole moment. So it is a net change in the dipole moment. So if one component has for example if we look isopropanol is something called like CH2 CH3 or OH. So in this we have a different kinds of dipole moment. So iodation, by getting the iodation, the molecule will be vibrated in different oils, and this there will be a net change in dipole by which we will get such kind of vibration modes. So this kind of vibration modes can be expressed by equation is called linear is called like 3 and 5 for linear molecule, 3 and minus 5, sorry, here 3 and minus 5 and 3 and minus 6. So this is for the linear molecule, and this is for non-linear, I mean which where you will get a lot of side groups. That is by this equation you will get by how many vibration modes are present in your molecule. Okay, so two things are cleared. So now we can discuss actually how the spectra can be explained. So once we will get the spectra from this radiation, from this spectroscopy, I mean the thing is that when the irradiation will be irradiated by the sample, and sample will get the information to the detector, and by Fourier transform we will get this kind of interferogram, and Fourier transform by this interferogram we can describe as a light of function by which we can get a lot of